part of the entire series. So here we are going to talk about how are we going to utilize the previous two models which we created. So this is the evaluation.ipynb. Here we are going to unzip our previous models which we had created. Here you can see using the NVIDIA SMA that we are using the GPU, and we will be installing all the required packages. This is one of our custom packages which we created, which helped us in making the demos. And you can also download it. It's open source. This is the code file from where we you can download demo videos, and this is the code file. This helps in the speeding up of CUDA. So here we are going to take this video and we are going to see of a particular frame on it. So it's what the supervision SV does. It provides you a frame. So as you can see, this is one of the football player field. Now we are again going to download some of our previous uh, packages, and once we are done with that, we are going to load our model. This is the model for the player object detection. uh, we create boxes and labels for the players, balls, etc. And what we plan to do is create an inference. So, as you had seen earlier, we are able to successfully predict where referees are, where goalkeeper is, and where the players are. The ball detection is very low, so the MAP is around zero point 0.3, so it might not be detected in all the frames, which is one of the challenges we are trying to face. We are trying to solve here, that what to do in case the ball is not detected and we are getting irrational movements from the ball. Uh, so one of our key things we wanted to do was video game style visualization, how it's in a FIFA video game. So for that, we are going to convert our rectangular boxes into ellipse annotators. So what's that going to provide us is this kind of a system where you are having just a second, all the players having a red, yellow, and blue colored circles in which they are standing. So you can see who the player is, what they are doing. Uh, Now, another part is player tracking. So we are here using ByteTrack to track each of the players. So now we are able to individually detect all the players here. So if you see here, you are able to see player number one, player number two, player number three, player number four, etc. Now, one of the key things is now since we have the players, we can see that all the players here. For example, there are two teams, one wearing green, one wearing red. There are many on the red players. There are we have two teams, players of red team and players of green team. We don't need to specifically even search for the goalkeeper and referee because we have already found them out earlier. So now what we need to do is just classify the players only. Players excludes goalkeepers into teams. So we for that we are going to use Siglip, UMAP, and K-means algorithm. As you can see here, we are able to fit it on the team on the basis of the colors of the uh, clothes they wear. So this is an example of a crop which we gathered from the previous thing, where from here we are going to use Siglip and we are going to calculate the embeddings for each of the crops. So you will be getting the some value of embedding for this crop, this crop, this crop. And now since you have similar embeddings on this, you will be able to, with the help of k-means, cluster this three similarly into a similar group. So UMAP helps in dimensionality reduction. So our n comma 768 becomes n comma 3, and with the two cluster division of k means, we are able to successfully see what are the two values it coincides to. This is a visualization. It's currently not. So the visualization of this looks something like this, where you can see that all the people are in red and all the people in blue can be easily classified as being different, and there's a clear boundary to identify this gap. The the next part comes in resolving that which goalkeeper is of which team, because since we already have references to goalkeepers, we don't know which team they belong to. So what we here try to do is that um, we try to keep the goalkeeper who is the closest to the team's centroid as the goalkeeper of that class. So if it's team one and it's closer to the team one, it's going to be, if it's team one, then it's going to be closer to the team one goal post. If it's of team two, then it's tends to be closer to the goal post of team two. Now these things are kind of uh, assumption which we are taking, because we know in real games goalkeepers can come out and play where they might overtake each other, they might tackle each other, but we are not considering those cases. This is simple heuristic which we are considering. So this is resolving all the goalkeeper team IDs code. And so here you will be able to see that we are able to successfully say that this goalkeeper belongs to the team blue. The next portion is of pitch detection. So what pitch detection means is we need to identify what are the points here, 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 and here, and be able to see, be able to scale the it to the entire football ground, so that we are able to clearly we are able to, using just one image, be able to clearly identify and provide a top down view of the entire football field of what's happening right now. So here we are able to collect this as key points. And one of the key things is that you will be seeing that most of the key points are not correct. Why is this the case? It's because it's a fast moving game, and key point of your previous might influence the key point of your next frame. So that's one of the issues. So which is why the model would also be saying that, hey, I'm not completely sure of this key point, which is why we are going to filter out all the low confidence key points here. Of wherever we have confidence of less than zero point 0.5, we are going to mask it. And so we are left with this uh, points, key points. It's currently also not completely correct, but it's something which can be doable and can be corrected with more data. So just providing a top-down view, this is our football ground. If you want to use something like this, you can use our uh, sports, what this is, our created sports package from the link provided to you earlier. And so this is how the lines are detected. So as you can see, these lines are detected very closely, but this line is a bit far away from what we expected usually. But these are the challenges which would be facing, and more data as we see, which is annotated, the errors would become less and less prone. So after using this, and these are just some of the helping bits in the code. You will be able to see a game like this here. And so we had this, and from this what we are able to create is where the blue team currently resides. So as you can see in both these frames, we are not seeing the red team people, we are only seeing the blue team people. So it helps us know that what strategy they might be following. Another is a Voronoi diagram. Here you can see what are the areas blue team is covering and what are the areas red team is covering. So here you can see that hey, this is the area covered by red team and this is the area covered by red team. So they might be planning on passing, while blue team has a player here, which means that they might be planning to have a goalkeeper kick the ball from here to here, while the players from here try to dash through and make a successful goal attempt. So these are some of the key things which you can note from here. Also, one of the key things you can see is that here, as I had said earlier, the goalkeeper is also uh, tracked as team red, and this is how the position of red team is. So you can join both this graph and this visualization and this visualization to get something like this. So now one of the issues is ball tracking. So we know that if the football is very hard to track. So one of the things which we are trying to do here is to make sure that the error in which we are tracking the ball decreases. So one of the thing is that the confidence should always be greater than zero point 0.5. We want to say that it's a football. And here what we try to do is we go through all the frames in the match and we try to find what are the positions of the ball, of the football. And just a second, so this is the going through the all the frames. And also one of the key things, if you see, the inference speed is just 33.3 milliseconds, so it can support live broadcasts. Okay. So now you can see the draw path. Uh, so you can see it's an x comma y plane, and wherever you are not able to see a value, it means that it wasn't able to track the football in that frame. This is truncated, but the whole thing contains tons of data. So it has value here, it has value here. So now what we are going to do about the missing frames which we have. So one of the things which we can do is just say that ball moved from position A to position B. But let's say if this is goes out to zero because of a misdetection, and it's a very high amount of distance travel within a very short period of time. So this is one of the challenges, and how we try to do is we try to use smoothing. So here we convert it into a simple path, and if you can see, this is the unsmoothed path with ball going everywhere, which is due to misdetections. Now, what we try to do here is we try to reduce all the outliers which we get with the ball detection. So here, in case we are not able to detect the ball, we say that the ball moved around 50 units somewhere along the line. And if here we see if the last position was valid, if no position is valid, then just use the current position which we have and it serves as the starting point of the game. Now, let's say if we got a position and it's much more than the distance threshold. So we say that this might this is very high this has very high chances of being a misdetection, and so we add a distance of 50 to the distance threshold. Now this keeps on piggybacking, so that once we get another real um, ball detection, football detection, so we can see that hey, let's just append this position because it's less than the distance threshold, and so we are able to get cleaned football tracking. So currently we are using the first max distance threshold as 250 and going through it. This could vary based on where your camera is angled and what's its distance from the football field. But if you are able to correctly use scaling and are able to get correct outputs from the key point detection, you might also be able to infer these values based on scaling of the entire football field, the distance between the camera and the football field where you are tracking, and be able to create your own, create a better max distance threshold for yourself. So that's it for now. Thank you, and hope you learned something new today. So overall, it was a great experience building this project. We were able to use YOLO model. We were able to use ByteTrack. We were able to do many small improvements in CUDA GPU, so that, for example, using the OS fragmentation checks, etc., it helped us move forward better. And football is a sport which all of our team members loves and we watch. So yeah, it was an amazing experience, and we might try to go ahead with building on this in future. So thank you.